Welcome to Simplified UPSC by PPP, where we listen, learn, and grow together. Detailed lecture notes in English and Hindi, plus practice questions for prelims and mains, only on our Telegram channel. Link in description. Like and subscribe for more.
Welcome to the Deep Dive. Today we are tackling one of the most mechanically fascinating and just profoundly destructive forces on our planet, the earthquake.
That's right. And our mission today is really to perform surgery on this source material, section 2.1 from the Simplified UPSC by PPP channel.
So not just a summary.
No, not at all. We're transforming this dense data into high-resolution, fact-dense knowledge. We want every single number, every specific term, to be absolutely cemented in your mind by the end of this.
Okay, think of this as your shortcut to mastery. We're distilling the core, the must-knows, and, the insights that turn memorization into real understanding.
And well, before we plunge into the Earth's engine room, so to speak, we have to give a moment of thanks.
Absolutely. If you value this kind of detailed analysis, we certainly do encourage you to join us as a YouTube member.
It's the fuel for this project.
It really is. It directly supports the team that produces these comprehensive study aids. Your support genuinely keeps us motivated to tackle the next big chapter.
And to our existing members, a really warm, dedicated shout-out. Your support is the backbone that makes these deep dives possible for the entire community. So, thank you.
Now, let's start with the sheer scale of this. Earthquakes are one of the most destructive natural hazards known. We're talking about the ability to wipe out buildings, infrastructure, in just seconds.
And it's that speed, that sudden impact that's so critical. The effect of an earthquake is, and we have to stress this, sudden.
No warning.
Almost none. Which is why accurate and exact prediction is still scientifically impossible. It makes mitigation our only real defense.
And when that impact hits, the consequences go way beyond just the physical destruction.
Exactly. At its core, an earthquake is the sudden shaking of the Earth's crust. But those ripples, they destabilize governments, they can paralyze economies, and they can completely fracture the social structure.
So to understand that, we have to start at the root, the very skin of the planet. Okay, let's unpack that. The foundational reason why the Earth's crust shakes in the first place, we have to go deeper than the surface.
And that takes us straight to the central framework of Earth science, the theory of plate tectonics.
Okay.
This theory explains that the Earth's surface isn't one solid piece. It's actually fractured into these gigantic rigid sections we call plates.
And these plates are always moving. They're not static. So what's pushing them? What's the engine?
The engine is deep inside, in the layer right underneath called the mantle. The movement is driven primarily by these incredibly powerful thermal convection currents.
Convection currents, like boiling water.
It's a great analogy. It's heat from the core moving outwards, creating this massive, slow-moving conveyor belt in the viscous mantle that forces the plates above to move and interact.
And it's at those interaction points, the boundaries, where all the action happens.
Yeah.
That's where the stress builds up.
Precisely. And there are three crucial ways they interact. Let's start with the first one, which is all about creation. Divergent boundaries.
Divergent, so they're pulling apart.
Exactly. The plates are literally pulling away from each other. And as they do, magma rises from the mantle to fill the gap, creating new crust.
And the classic example of this?
The Mid-Atlantic Ridge. It's a massive underwater mountain range that basically splits the entire Atlantic Ocean north to south.
And the source material gives us a specific number for this, which is fascinating.
Yes, and it's a number you have to know. The spreading rate along that ridge averages about 2.5 centimeters per year.
2.5 centimeters. That's what the speed your fingernails grow.
Pretty much. But it's the Earth generating an entire ocean floor at that rate. To put that in perspective, that's 25 kilometers of new crust every million years.
Wow. Okay, so that's creation. What about the opposite, the destructive side?
That's mechanism 2, convergent boundaries. This is where the real force builds up.
These are the collision zones. The plates are pushing against each other.
Right, and usually the denser plate is forced down or subducted under the other one.
And what's the result?
The result is that crust is destroyed. It's recycled back into the mantle. And because these collisions are so violent, they create the most powerful earthquakes and most of the world's volcanoes.
The examples are unforgettable, right?
Absolutely. Globally, you have the Ring of Fire encircling the Pacific. And of course, the most spectacular example is the ongoing formation of the Himalayan mountain range. That is literally two continents colliding.
Incredible. Okay, so we have creation, we have destruction. What's the third type?
The third type is transformational boundaries. Think of this as a sideways grind.
So no new crust, no crust destroyed.
Exactly. The plates are sliding sideways horizontally past each other. The crust is neither produced nor destroyed. But the friction, the sheer stress, is immense, and it generates these very powerful, often shallow earthquakes.
And the most famous example of this has to be
The San Andreas Fault in California. The source material pinpoints it slicing right through the Carrizo Plain. Understanding these three motions, divergent, convergent, transformational, is really the first step to mastering this.
Okay, so that tells us where the energy builds up. Now, how is it released? Let's get into the anatomy of the event itself.
Right, the terminology. We have to start with the point of origin, the precise spot where the slip along a fault actually begins.
And that's underneath the surface.
Yes. That point is called the phokias, or the hypocenter. This is where the accumulated strain, which has gone beyond the rock's maximum supportable strain, is suddenly released.
So the focus is the real origin. But the point we always hear about in the news is the S.
The epicenter. And that is the point on the Earth's surface directly above the focus. The shaking you feel is directly related to the epicentral distance, how far you are from that spot.
And the depth of the focus matters too, right? The focal depth.
This is crucial. It determines how we classify the earthquake. But before we get to that, let's just quickly link this to another hazard. Tsunamis.
The source makes a direct connection here.
It does. It states that fault movements on the seafloor, when they happen with an earthquake, are the most common cause of tsunamis. That sudden vertical displacement of the seafloor is what pushes up that massive column of water.
Frightening. Okay, so let's talk about the energy itself, the seismic waves.
Right. These are the messengers of destruction. We divide them into two main types: body waves and surface waves.
Body waves, so they travel through the body of the Earth.
Exactly. They're fast, and they're the first to be detected. We split them into P waves, or primary waves, and S waves, secondary waves.
And they move incredibly fast.
Yeah.
The numbers here are important.
Very. P waves are the fastest. They travel at about 6 kilometers per second.
6,000 meters every second. That's hard to even imagine.
It is. And then the S waves follow behind. They travel a bit slower at about 4 kilometers per second.
And they can only travel through solids, right?
Correct. Which is a key piece of evidence for how we know the Earth's outer core is liquid. But for our purposes, that speed difference, that 2 kilometer per second lag, is the fundamental tool seismologists use.
Because the longer the gap between the P wave and S wave arriving,
The farther away the earthquake is. By combining the data from 3 or more seismic stations, they can triangulate and pinpoint the epicenter with incredible accuracy. That's the practical application of knowing those two speeds.
Okay, so those are the body waves. What happens when they reach the surface?
They transform into the slower, but often much more destructive, surface waves.
And these are the ones that do the visible damage.
These are the ones, they vibrate the ground horizontally and vertically. Their long, rolling motion is what causes the swaying of tall buildings, and that visible wave motion you can sometimes see.
Let's circle back to focal depth now, because that seems really important for risk.
It is. We have 3 classifications. The most critical for disaster planning is the shallow focused earthquake,
Shallow is defined as
less than 60 kilometers deep. And these are generally the most damaging because the energy is released so close to the surface, the ground motion is just maximized.
and deeper than that.
We have medium focus, which is between 60 and 300 kilometers, and then deep focus, which is between 300 and 700 kilometers deep. These can still be huge events, but the energy spreads out so much by the time it reaches the surface that the intensity is often much lower.
All right, now that we have the anatomy, how do we quantify it? There are 2 different scales, and it's so important to get the distinction right.
Absolutely vital. They measure 2 completely different things.
Let's start with the one everyone's heard of, magnitude. The Richter scale.
Right. The Richter scale, developed by Charles Richter, it measures the total energy release at the source at the phokias.
And it's logarithmic. That's the key detail.
That is the key. A jump from, say, a 6.5 to a 7.5 isn't just a little bit more shaking. It's about 30 times more energy being released.
30 times.
Yes. So the takeaway is, an earthquake has only one magnitude. It's a constant for that event, no matter where you measure it from.
Okay, so that's magnitude. But then there's intensity.
And intensity is completely different. It's about the human and structural experience of the earthquake. It's localized.
This is the modified Mercalli scale.
Correct. It measures the effects or the damage at a specific location. So a single earthquake will have many different intensity values depending on how close you are, the local geology, building quality, and so on.
And the source gives us some history here.
It does. The concept was developed back in 1902. The scale uses Roman numerals from I, which is not felt, all the way up to 12.
And what does 12 represent? That must be total devastation.
It is. Intensity 12 is described as total collapse, general panic. It means the ground motion is so violent that even well-engineered structures are failing. It's a complete breakdown.
So magnitude is the energy of the bomb. Intensity is the damage your specific house took.
That's a perfect way to put it. They are linked, but they're separate measures.
And before we move on, we have to reiterate the most important point for disaster management: predictability.
This is non-negotiable. The impact is sudden. There's hardly any warning. And this makes accurate, exact predictions of earthquakes currently impossible.
The methods that have been suggested are controversial.
Highly controversial. So all our energy, all our focus has to be on preparation and mitigation, not on waiting for a prediction that isn't coming. And that unpredictability makes understanding the regional vulnerability profile absolutely essential, especially for a country like India.
Right. India's specific geological context, the source is very clear on this. It falls prominently on the Alpine Himalayan belt,
Which is this massive geological seam where the Indian plate is colliding with the Eurasian plate.
So this is a convergent boundary. We covered that.
A very active one. The Indian plate is continuously thrusting underneath the Eurasian plate.
And there's a specific rate for that movement, another one of those critical data points.
Yes, and you must remember this number. The motion is happening at a rate of 5 centimeters per year.
5 centimeters. Every single year. That is an unbelievable amount of pressure building up.
It's the single most important factor driving India's seismic risk. This constant movement builds up tremendous stress in the rock, which accumulates for decades or centuries, and then is suddenly released. The Himalayas themselves are the result of this process.
And to manage this, India has been mapped into seismic zones. Let's walk through that map.
Right. The country is divided into 4 zones: Zone 2, 3, 4, and V. This dictates everything from building codes to preparedness.
Let's start at the top, the highest risk.
That's Zone V. It's shown in red on the maps. This is the very high-risk zone, the most vulnerable, where we can see earthquakes of magnitude 8 or even higher. It covers the northeast, parts of Jammu and Kashmir, Himachal, Uttarakhand.
The Himalayan frontier, essentially.
Precisely. Now, Zone 4 is the high-risk zone. And what's crucial to remember here is that New Delhi, the capital city, lies in Zone 4.
So the political and economic heart of the country is in a high-risk zone.
Exactly. The challenge of keeping that city resilient is immense.
Okay, then we have Zone 3.
Zone 3 is moderate risk, but it's a huge area. Much of peninsular India falls into this zone, including major cities like Mumbai and Chennai. So while the risk is moderate, the potential impact is still massive.
And finally, the lowest risk.
That's Zone 2, which covers the southern part of the peninsula. It's still subject to seismic disturbances, but generally up to a maximum of about magnitude 4.9.
And it's important to ground this in history, right? This isn't just theoretical.
Not at all. We have to remember events like Latur, Maharashtra in 1993, a magnitude 6.3 earthquake. That was a shock because it was deep in the supposedly stable Deccan Plateau.
And of course, Bhuj.
The Bhuj earthquake in Gujarat, 2001, a magnitude 6.9 catastrophe. That event really demonstrated the scale of destruction possible outside the main Himalayan belt.
And we also have to think about cross-border events.
Yes, like the Muzaffarabad earthquake in 2005, magnitude 7.4. It was centered in Pakistan, but had a severe impact on Jammu and Kashmir. Tectonic plates don't respect political borders.
So let's talk about those consequences. The immediate damage is obvious: buildings, infrastructure.
Bridges, roads, railways, water towers, power plants, the lifelines of a modern city, they all fail.
But the danger doesn't stop when the shaking stops.
No. Aftershocks are a huge threat. They can go on for days or weeks, bringing down structures that were already weakened by the main shock.
And then there are the secondary effects, the cascading disasters.
Fires from broken gas lines, landslides that block rivers and cause floods, and a big modern risk is damage to industrial facilities, which can lead to dangerous chemical spills. It just compounds the crisis. So given that we can't predict them, the entire focus has to shift to disaster management and mitigation.
And mitigation isn't just about what you do during the shaking. It's about what you do before.
Exactly. It's all the activities taken beforehand to reduce human and property losses. And it's not just physical. It's about reducing the economic and social vulnerabilities, too.
So where do we start? What are the key strategies?
The foundation is planning and mapping. You have to use hazard mapping to locate high-risk areas, areas prone to shaking, landslides, and so on.
And then avoid building there.
That's the first rule. Avoid building settlements in those areas, especially a place that's marked as Zone V. That mapping is the essential tool for everything else.
What about public preparedness?
That's about awareness campaigns and having disaster management plans ready at the household and community level. Every single person should know the basic drop, cover, and hold procedure.
Okay, now let's get into the engineering side. Structural safety. Retrofitting.
This is critical, strengthening existing weak structures. But for new construction, it's about strict adherence to building codes and bylaws, like those from the Bureau of Indian Standards.
And the source mentions some specific structural requirements.
Yes, for masonry buildings, a lintel band is key. It's a reinforced concrete band at the top of the doors and windows that ties the walls together and stops them from bowing out during shaking.
What else? The foundation.
A stiff foundation is crucial. It helps the whole building move as one unit with the ground. And making sure the roof is securely connected to the walls is another non-negotiable point.
And the ground itself makes a difference. The soil type.
A huge difference. You must do a soil analysis. Buildings on soft soil, like alluvial soil, experience much more violent shaking. The ground acts like jelly and amplifies the waves.
Whereas building on solid rock.
Building on BFE is much safer. You still get a sharp rumbling, but the energy isn't amplified. So your building design has to account for the ground underneath it.
It all comes back to planning.
It all comes back to smart land use practices, especially in coastal areas where you have the added risk of tsunamis from those offshore fault movements.
Okay, we've covered the mechanics, the scale, the mitigation. Now let's put it all together. Let's run through some UPSC-style questions and synthesize answers using only the facts we've discussed.
Great idea. This helps lock in the knowledge.
Okay, review question 1. What are earthquakes? And list out the causes.
Right. An earthquake is the sudden shaking of the Earth's crust. The primary cause is explained by the theory of plate tectonics, driven by thermal convection currents in the mantle.
And you'd have to list the 3 boundary types.
Absolutely. You must detail divergent boundaries, where new crust is formed, like the mid-Atlantic ridge spreading at 2.5 centimeter. Convergent, where crust is destroyed, forming places like the Himalayas, and transformational, where plates slide sideways, like the San Andreas Fault.
And for a full answer, you'd need the specific Indian context.
You must mention it. The primary cause in India is the convergent boundary, where the Indian plate is thrusting underneath the Eurasian plate at a speed of 5 centimeters per year, causing immense stress to accumulate.
Perfect. Next question. Differentiate between magnitude and intensity of an earthquake. How are they measured?
Okay, the key difference is what they measure. Magnitude, measured on the logarithmic Richter scale, quantifies the total energy released at the focus. It's a single constant number for the event.
And intensity is the opposite in a way.
Exactly. Intensity, measured by the modified Mercalli scale, measures the localized effects or damage. It varies from place to place. It's measured from I to 12, where 12 signifies total collapse and general panic.
So one measures the cause, the other measures the effect.
Precisely.
Last one. Review question 3. Identify 3 major mitigation measures to reduce earthquake risk.
Okay, number 1, hazard mapping. Using it to guide land use practices and restrict development in high-risk areas like Zone V.
Number 2.
Structural safety. That means enforcing building codes that require things like a lintel band and a stiff foundation, and retrofitting older, weaker buildings to resist the force of P waves and S waves.
And the 3rd, the human element.
Right. Community preparedness. That means continuous awareness campaigns and disaster management plans so that everyone, especially in a place like New Delhi in Zone 4, knows exactly what to do, like drop, cover, and hold, and is prepared for aftershocks and secondary disasters.
And that brings us to the end of our deep dive. The big takeaway for me is that contrast between the slow, steady mechanism, that 5 centimeters per year push, and the sudden, violent result.
It's all connected. And that leads to a final thought for you to consider. Given that we know scientifically that exact earthquake prediction is currently impossible, how does a society reconcile the constant need for development and construction, especially in high-risk zones like New Delhi or Mumbai?
With the guaranteed, measurable, and relentless accumulation of stress along those tectonic boundaries.
Exactly. It changes the entire problem from one of prediction to one of permanent, resilient engineering and preparedness.
A question to live with, not just to answer. Thank you for joining us for this incredibly detailed deep dive.
And our deepest gratitude, once again, to the Simplified UPSC by PPP members. Your support is what allows us to do this. Study well, and we'll see you on the next deep dive.
Thanks for watching. Follow us on Telegram and Instagram. Don't forget to like, share, and subscribe.